Welcome back. Now we'll continue with Module 8 by starting to look at reactions. So heat of reaction, we know that chemical reactions are another really large source for enthalpy change. A lot of energy has to be used to break and reform chemical bonds within molecules, and this is going to be really important for us to keep track of as we do energy balances with chemicals. Now, most commonly, we report this energy change for a reaction as enthalpy of reaction, but it also is possible that you may want to at some point use internal energy, change of reaction, or Gibbs energy of reaction, or any of our energy terms. But for now, we're going to just stick with delta H of reaction. Now, the enthalpy of reaction is going to have units. It's usually something like kilojoules per mole. And what I want to really emphasize to you is that per mole means whatever has a stoichiometric coefficient of 1 in the reaction. So if you had something like A plus 2B makes C, then this would be kilojoules per mole of A, or kilojoules per mole of C that's formed, or kilojoules per 2 moles of B that react. So you need to keep track of what they mean by mole and exactly the way that the reaction is written down. Now, there are two special categories of reactions we need to deal with. The first of these is the formation reaction. A formation reaction is the reaction that forms a molecule from its elemental constituents as they would normally occur in nature. So, for instance, ammonia. It's NH3, so it's made out of nitrogen and hydrogen. Both of those in nature are normally gas. So this would be the reaction of 1/2 of a nitrogen gas molecule plus 1.5 hydrogen gas molecules forming NH3. Sodium carbonate is Na2CO3, so I need 2 sodium atoms, 1 carbon, and 3 oxygen. And so sodium appears in nature as a solid, carbon also is a solid, and oxygen is a gas. And so we get these various formation reactions. Now some things like helium are simply the elemental form, right? So therefore that formation reaction would simply be helium as a gas makes helium as a gas. Notice that always these are based on 1 as the stoichiometric coefficient for the molecule formed. That means you can end up with some pretty crazy coefficients on those molecules that are the reactants to form this product. That's okay. We're not saying that this is going to be really the way the chemical is made. This is just simply a formation reaction that would make this. Now, the standard heat of formation is typically what you'll be able to find in data books. It's going to be the enthalpy change for the formation reaction if the given compound was at 25 degrees C in 1 atmosphere. Sometimes it's not that temperature and pressure, and so you'll want to read in the data booklet to see exactly what they used. But this is going to be, again, an opportunity for us to combine this with a hypothetical path if our reaction does not occur at 25 C in 1 atmosphere. So data can be found, a lot of textbook appendices, Perry's Handbook, if you're a member of AICHE, student membership is free and you can get access to that online. This table segment below comes from the Felder and Rousseau textbook. What you'll see is in table B1 from that book for various compounds. They give a lot of different data, but way over at the end there's delta HF, little superscript not, and then there's some things that tell you go look at a table or go look at a footnote and see what the standard is. When they use a little not there, that means that it's a standard value, and the references tell you what those standards are. In this case, it is 25 C in 1 atmosphere. Now, for some of these, there's going to be multiple substances listed. So you look at acetic acid, and it's got the liquid state and the gas state, because it could be either one of those at 25 degrees C in 1 atmosphere, and so therefore you need to be able to know which product you are trying to make. Okay. If you don't have the one you want, then you can just create a path. You can go through the heat of vaporization or whatever you need and get exactly the delta H that you are wanting to do using hypothetical paths. Now, Hess's law you probably have encountered in a chemistry class. Hess's law says, if the stoichiometric equation for reaction 1 can be obtained by algebraic operations on stoichiometric equations for reactions 2, 3, whatever, then the heat of reaction for reaction 1 can be obtained using exactly the same algebraic operations on reactions 1, 2, 3, 4, whatever. So, just a little example here. If, let's say you knew these particular heats of reaction, C2H6 plus 7/2 of an O2 makes 2 CO2s plus 3 H2Os with a heat of reaction of negative 1560 kilojoules per mole. And carbon plus oxygen makes CO2 with a heat of reaction of negative 393 kilojoules per mole. And hydrogen plus half an oxygen makes H2O with a heat of reaction of negative 286 kilojoules per mole. So if you have that information, can you find the heat of reaction for 2 carbons plus 3 hydrogens forming C2H6? Okay. So go through and play the little game. So first of all, I'm trying to form C2H6. So this one is the product in what I'm trying to find. So I'll just multiply this whole thing through by a -1. In other words, I'll switch the order. So if I switch the order, I also will switch the sign on the heat of reaction. So I end up with this reaction has heat of reaction positive 1,560 kilojoules per mole. For this one here, well, I'm wanting 2 carbons. So this reaction is for 1 carbon. Let me just multiply it by 2, and I'll do that to everything in that reaction. And I'm looking at this realizing, no, that's okay. So 2, yeah, that's correct. Okay, so 2 CO2s. Everything's by 2, which means I'm going to multiply the negative 393 times 2. And then finally I'm going to add 3 H2s. All right, so I want 3 of these, so I'm going to do 3 times this reaction and 3 times this heat of reaction. Now, based on this, if I add these up, hopefully I'll get this reaction. So let's check that first. I have 2 CO2s, 2 CO2s. They're on opposite sides, so they'll cancel. I have 3 H2Os, 3 H2Os, they'll cancel. On this, I have 2 and 1.5, so I have 3.5 oxygens. Over here, I have 3.5 oxygens. I'm left with 2 carbons plus 3 H2s makes C2H6. So I have combined these reactions to create this reaction. So I now go through and I just added these, so now I'll add these. And the sum of these tells me that the heat of reaction for this is negative 85 kilojoules per mole. So if I want to do enthalpy of reaction from enthalpy of formation, I can just simply use Hess's law and the standard enthalpy of formation to get a standard heat of reaction. One thing that you will need to note. When you're looking up heat of formation of an elemental species, it typically isn't there. So remember helium gas? It is an element, right? So the heat of formation for that is going to be 0. I have to put no energy into turning helium gas into helium gas. So therefore, the heat of formation for an elemental species will always be 0. So based on that, can we find the heat of reaction for the dehydrogenation of ethane? So basically, this is breaking ethane into ethylene plus hydrogen gas. So I want to find data. So I go to a data table, and you can use any data table that you have available. But for C2H6, I found negative 84.67 kilojoules per mole. For C2H4, I found positive 52.28 kilojoules per mole. And hydrogen, it's an element. It's 0 kilojoules per mole, or whatever other units you wish to work with. It's still 0. So my answer, I'm forming these, so I just simply take these and add them. I am breaking apart this to make these, so therefore I subtract that heat of reaction. So the heat of reaction of the products, or heat of formation of the products, minus the heat of formation of the reactants. And that tells me that I have a positive 137 kilojoules per mole. Now, one word here. You probably vaguely remember this from a chemistry class. Exothermic reactions and endothermic reactions. So one of my examples had a negative enthalpy of reaction. The next one had a positive enthalpy of reaction. These are, one was exothermic, one was endothermic. An exothermic reaction is the one that releases energy. It's going to be the ones with a negative enthalpy of reaction. These are the things that you use like when you make a chemical hand warmer. Okay? These are reactions that are releasing energy. If you're trying to do the reaction at constant temperature, you're going to have to remove heat from that process. Now, if the heat of reaction is positive, it's going to be kind of just the opposite, right? So these are going to absorb energy. They are going to have a positive enthalpy of reaction. And if I want to keep the reaction at a constant temperature, I have to keep adding heat to the system. A lot of times we use endothermic chemical reactions in a chemical cold pack. So let's very briefly look at heats of combustion. I said there were two ways that we used Hess's law. One was using heats of formation, one with heats of combustion. So this is actually going to be available also. Sometimes it's even easier to find than heat of formation data. But it isn't always available. When you have it, it's great, not always available. So the heat of combustion in the Felder and Rousseau textbook is the column right next to heat of formation. This is the enthalpy for the combustion of this chemical. For complete combustion of 1 mole of material with the stoichiometric amount of oxygen that produces CO2 and H2O and any other gases that are appropriate for that chemical. So in this case, now I'm breaking these apart. So it's the opposite of forming them, right? I'm going to take this molecule and I'm going to break it apart. So here I'm going to take reactants minus products when I use heat of combustion and Hess's law. With formation, remember, I'm putting them together, so it's products minus reactants. Be sure you get that sign correct because it does make a big difference on whether you're predicting an exothermic or an endothermic reaction. So let's look very briefly at an example for this one. Let's calculate the standard enthalpy of reaction for ammonia plus oxygen to make NO plus water. So let's do this both ways. First, using heats of formation. Okay, so I just look up all the numbers for heats of formation, and here I have my products, or NO and H2O, and then subtract my reactants, NH3 and O2. O2 is elemental, so that one has a value of 0. And be sure to include the stoichiometric coefficient. So 4 times 90.37, 6 times negative 241.83, so forth. And I get negative 904.74 kilojoules per mole. My other choice is to look up heats of combustion and take these minus this. Now everything goes just fine except nitrogen. Nitrogen products are a problem. Whenever you have nitrogen in your reaction, heat of combustion is going to be a dicey proposition. It's great on hydrocarbons, not so awesome when you have nitrogen. The problem is that what is nitrogen forming when it reacts with oxygen? In this case, this is a combustion reaction, correct? Sort of. I'm reacting ammonia with oxygen, and it's making these. But this time it made NO. Maybe it makes NO2 or N2O or N2. Nitrogen can form so many different compounds, it usually is not included in heats of combustion. So, one more little quickie here. What's the enthalpy change for 5 moles of ammonia at 25 degrees C in 1 atmosphere reacting with oxygen to form NO and H2O? So, not a problem, 5 moles of NH3. I have the enthalpy of reaction. I calculated it based on heats of formation. But notice the stoichiometric coefficients. I have to pay careful attention to those. So I have the heat of reaction, negative 904.74 kilojoules per mole. The reaction was written as 4NH3 plus 5O2 plus 4NO plus 6H2O. So, to figure out the actual enthalpy change, I have 5 moles of NH3. This is written as negative 904.74 kilojoules per mole, but that's a reaction mole. I don't have a stoichiometric coefficient of 1 anywhere in here, so I like to use this as like a conversion factor. So 1 mole in the reaction means 4 moles of NH3 are reacting. So divide by your stoichiometric coefficient, and this tells me then 5/4 of this number, or negative 1131 kilojoules, is going to be the enthalpy change for this reaction. Now in the next video we're going to look at another little enthalpy reaction problem, and then we're also going to talk briefly about fuels.